much more advanced things are coming, and those are called the fundamental theorem of calculus. And I will start with traditionally the second part, but the reason is that it is easier to explain, and I like to refer to the second part explaining the first part. So the first attempt I will make is to look at this symbol again, this concept, and try to understand what this is about. Well, what I see here is a lot of symbols, right? I told you that we so far understand dx as just symbol there, and we are not trying to manipulate dx. A is a number, and b is a number, and the result is again a number, and the resulting number, the integral, depends on a and depends on b. Right? So what we can say is that what we see here is a function of a and b. So it can be thought of as a function of two variables. And those two are independent variables. Right? There is no relation, we assume, between a and b. And that will be the subject of our study in the next semester in multivariable calculus. What can we say about a function of two variables as we think about the definite integral? But it's very easy to make a function of two variables a function of one variable. Right? We just fix one of them. And that's what we will practice today. We will fix one of those, and the standard way is to fix the top one. Oh, sorry, to fix the bottom and to keep b the variable. Right? So now we keep thinking about this as a function of that b, and a is always the same. Think of a as 0 if you want it. Now, what about x? Is x a variable? Well, definitely it is, right? But is this result going to depend on x?
It's only plugging for x.
Well, the problem is that you cannot take x equals 1 and plug it into this formula. It won't make any sense, right? So the meaning of this x is very technical, meaning it serves for notation purposes, but it doesn't play any essential role for computation of this integral. So I will come back to that later, but essentially the whole symbol is only a function of two variables, is only a function of these two limits. So we will look at this function now of new variable. So what is going to be the variable? Let's call it t. I will make the upper limit a variable. I will keep the lower limit a constant, and I will integrate f of x dx. Now the result is, let's call it g of t, a function of t. Right, so we are making this step to consider this as abstract quantity and study it as a function. And then, what can we say about this function? The simplest way to say something about this function is to compute the function. Right? But we are not ready yet to compute. We don't have any way to compute the function yet. And the second part of the fundamental theorem of calculus will be about computation. But the first part is not. It is about finding derivative of this function. So that's the curious part about this particular function, that it's easy to find the derivative, although it's not easy to compute the function itself. So sometimes it's easier to find derivative of something rather than something itself. Here's the, how do we find the derivative? Well, by definition. All right, so what is the derivative of g? by definition, right? It's limit, right? Limit as delta t goes to 0.
G plus delta t minus g t.
That's exactly right. Change of g over interval delta t divided by the length of the interval. Now, what we really have to practice now is finding limit, right? And you did practice finding limit in calculus 1. And the problem is that you practiced that when the formula here was a nice expression, like a polynomial divided by a polynomial, exponential divided by logarithm, this kind of stuff, right? Today we don't have any explicit expression because we cannot find the formula for g. We cannot possibly find it because f is unknown. So what we only can do is we can plug this integral into the formula. And the numerator becomes g of t plus delta t. So I have to plug g plus delta t into that expression. So I have to integrate from a to t plus delta t. And then I have to subtract the integral from a to t, the same function. And of course divide by delta t. Now what else can I do? Well, again, I cannot compute any of these two, but I can simplify the numerator. And that is by what? By which property? By additivity. So I'm integrating the same function over intervals, and those two intervals happen to have the same bound. So my limit is going to be limit of integral. So what should I put here? Will it go from t to delta t? F of x dx. And I have to divide by delta t. All right. Now, what we will practice for the whole semester is playing the game of interpretation of what we do from different points of view. I will explain why we will do it, and this is now a good example of why you should practice that. And what we will do now is I will try to interpret this geometrically. So I will sketch something pretending it's a graph of f. So it goes from a to some t. And the graph is the graph of the function f. This is x-axis, this is y-axis. And what is it that I'm subtracting? I'm subtracting the integral from a to t. What is it geometrically? It's the area below the graph over the integral from a to t. Right? Now, what is the first integral? It is also the area below the same graph over a different integral. Right? What is that new integral? It's from a to t plus delta t. I don't know. And that's exactly what I'm trying to verify. Right? So my graph continues, and I'm subtracting this area from this bigger area. Right? And that's exactly the quantity in denominator. So when you look at it geometrically, you see that the difference is exactly the area here below these two, or between these two vertical lines, right? So the result is the integral of the same function f over an integral from t plus delta t. Oh, from t to t plus delta t. Right? And not from t to delta t. So, that's one of the reasons you should change the point of view from clearly algebraic to geometric, and sometimes to physics. Maybe think about distance problem, interpret each integral in terms of the distance, and figure out that we are measuring here the distance over that period of time, subtracted from the distance over that period of time, and the result is definitely a distance traveled during the time from t to t plus delta t. So, at this point, it's just a verification that you used the formulas correctly. And yes, sometimes pure algebra can be confusing, and you may make mistake like this. And that's okay. What you have to deal with is whether you can check and verify that you did is correct or not by other means. Alright, so now once we simplified the integral, what else can we do? Well, again, the problem is that you cannot apply the standard techniques from calculus 1 of computing the limit. The only thing we can do now is interpret this numerator geometrically and see what that means. And what that means is the area that shows up in numerator is area of this column, and what you
Would you put in the factor that it's with this delta t? And then
yes, exactly. So the width of this column is exactly delta t. Right? And you take this area, divide by the width. If the area was an area of rectangle, the result will clearly be the height of rectangle. But what we see is not exactly rectangle, so we cannot say this fraction is exactly equal to something. But when we look at the limit, then we can say something, right? As delta t goes to 0, we expect the shape to resemble the shape of rectangle better and better. So the division of the area by delta t will result in the height with better and better precision. So that means the limit is going to be the height. And what's the height? All right, so what happens when we take delta t to 0? This point moves to the left, right? It changes, but that point t stays the same. As delta t goes to 0, t doesn't change at all. So the left side of the rectangle, of the shape, not rectangle, but the shape, is always the same, and the height is going to be equal to the value of f at that point t. And that's it. That's exact computation of the limit. Right? And we never used any properties like L'Hopital's rule or any algebraic manipulations. Although we did one manipulation with the integral.